This is a demonstration of the creation of a BGA ball map using the Cadence Orbit.io design environment. In this example, the ball map will be created from an existing die with a fixed pinout. The results of this exercise is the creation of an Excel ball map like this one showing, and a physical layout for SIP Layout XL for physical implementation. The ball symbol may also be exported to DEHDL for a PCB flow. The initial ball array that I load is an Orbit.io file created by importing an Allegro DRA file and adding a pin personality pattern. No nets are included. The balls are colored with the personality colors, and here are the personalities for general signal, power and ground, and differential pair signal, power and ground pins. I import the die by reading a die abstract generated by either Encounter or Virtuoso. I add the die to the BGA, then move it to the BGA center. I create interfaces and associate them to the existing nets of the die. Here I create a SerDes interface with 8 diff pairs or 16 pins. I use this form to associate the existing nets in the die with the interface. Notice how the pins are highlighted in the lower right corner of the die. The nets were already assigned to the bumps, so were highlighted when they were associated with this new interface. I could create each of the interfaces using this form, but for this movie, I will export a CSV file and create the remaining interfaces and net associations there and reload it. Here you see the CSV file with the net names in the left column and the interface names in the right column. The only interface defined thus far is the SerDes interface I created in the GUI, so I fill in the remaining interfaces. Now I load the file back into Orbit.io and see the interfaces highlighted in the die. I will now use bundles to create the connectivity to the package. The starting into the bundle is selected from the interfaces on the die. In this case, I'll start with the SerDes interface, and the destination pins in the package are those that have the signal diff pair personality. The bundle preserves the order of the nets as it flows from the die to the package balls. It also understands differential pairs and can place them vertically, horizontally, and diagonally. The crossbars and colors make it easy to identify each differential pair. I fast forward through the creation of the remaining bundles. The initial package I loaded had no nets, so as I create these bundles, nets are created and attached to the balls. If you start with a package that has existing nets, Orbit.io provides a mechanism to map these nets to the nets of the die. Bundling provides the initial ball map assignment. I now use die breakout feasibility routing to fine-tune the order of the nets in the bundle. I select several bundles at a time to run the breakout routing. Each pin has been given a routing rule indicating layer, spacing, and width of the routes. By performing the feasibility routing, I can see if the net ordering in the bundle can be broken out or not. When I zoom in, I see several spots that couldn't be routed, so I use this table to refine the breakout order of the nets. Note that I do not change the bump pin assignment, just the order they are broken out of the die. When I reroute the bundle, I see that it can be routed with the new bundle pin order. I can also route on multiple layers if needed. In some cases, the routing completed, but I changed the order to improve the breakout results. Because I changed the order of the nets entering the bundles on the die end, a number of net crossings have been created on the package end. So I optimized the pin assignments to the nets based on the new net ordering. This process optimizes the net assignments to the balls on the package and improves routability of the package. The initial ball map is now completed. I export an XML file for viewing in Excel. The net names and interface colors are preserved, and a key is provided here on the right side. This ball map is useful for reports, documentation, and design reviews. Of even greater value, though, is the ability to drive this design into SIP Layout Package Design environment to begin the implementation process. The BGA, the die, the nets, the bundles, and the diff pair definitions are all imported. I can use the flow planning functionality to fine-tune the placement of the bundles. When I open the Constraint Manager, you can see the differential pair definitions that were made in Orbit.io. All I need to do is set the differential pair spacing and width rules in Constraint Manager. I now use the Auto Interactive Breakout utility to create the fan-out routing for each of the die pins, beginning with the differential pair lines. I then will do the remaining breakout routes one side of the die at a time. Because we planned the breakout order on the die and the ball assignments to the package in Orbit.io, the routing job on the package is much easier. You can see here the results of the breakout routing for one of the bundles. Finally, I use the Advanced Package Router to complete the routing of this package. It connects from the breakout routes to the balls, inserting vias to drop from the top layer to the ball layer. I have shown how you can use Orbit.io to create a ball map array from an existing die with a fixed bump pattern. This ball map was used to generate an Excel ball map for use in design reviews and documentation. The resulting die and package configuration was also imported into SIP layout for routing implementation of the package substrate. I demonstrated the use of the auto-interactive breakout utility and the advanced package routing tool to route all the signals in the package. If you would like to learn more of how Orbit.io can help you in your IC package planning and implementation, please contact your Cadence sales representative.